most of our life, and definitely for this course, we are only worried about real valued randoms. Once we're talking about these random variables, it makes sense to talk about, once you do a random experiment, how much do you supposed to get as an outcome, right? How much? It could be money, it could be how many people, how many heads, how much number. So this expectation is a natural question, and we mathematically define what we mean by expectation. It was a very, very feeble indicator of what your random variable was. Another thing which is required is called variance. Again, so both of them, knowing expectation and variance, do I know the random variable? If I give you the expectation and variance, does that fix the random variable? Clearly no, right? So you should be able to construct examples of two random variables which have same expectation, same variance, but still they are far apart. So, okay, so let me just give you an idea again. Don't worry about the course, but just to understand these things. So expectation of X was E of X. What was variance? Right, but you know, E of X you have already calculated. So variance of X is essentially expectation of X square, right? And that means you can think of generalizing it. You can talk about expectation of X cube, you can talk about expectation of X4, so on and so forth. These are called moments. Again, for this course, you don't have to worry about it, but this is the idea. In this way, you can get more and more information about the random variable. So expectation is the first moment, variation is related to the second moment, then you can have third moment, fourth moment, so on and so forth. Right? This is how we try to gain more and more information about the random variable given to you. Okay, this is just to get the idea of why all these things are done, right? And since this point is very, very important, again, I would like to emphasize this, why normal is normal. So can someone tell me, why do we like normal distribution so much? Okay, so I understand that your intuition is correct, but I want to clarify a few points, right? The number of points in the sample space are not tending to infinity. Okay, first thing is you pick a distribution, and that distribution, the strength of the normal distribution is whatever distribution you want to pick, it's up to you. It could be Bernoulli, it could be binomial itself, it could be any distribution which you like, where your sample space is fixed, right? And exactly, what goes to infinity is the number of times you repeat this experiment. Okay, you have an experiment where the distribution is fixed, and as you repeat that experiment multiple times, you calculate the average of the random, right? So I have a random variable X in my mind, and the distribution which it follows is something I have no control over. Remember, it was like a person having cancer in something, and it need not be something which has only 0 or 1, right? It could be something which has value, random variable which has value 0, 1, 2. When I say someone has cancer, what is the random variable I'm talking about? The indicator random variable, right? Which is 1 if the person has cancer, 0 if the person doesn't have cancer, right? Generally, that is how you transform a yes/no question into a random variable, but it need not be. It could be something which has value 0, 1, 2. So sample space is fixed, need not have infinite numbers, but it can have any distribution. Now you take multiple copies of this experiment. Now, here is a small thing which I did not emphasize last time, but what we want is that the time I do the second experiment, it should not depend on what I did in my first experiment. This is what we call independent, that these random variables x1, x2 do not depend on each other. And I will formalize it. That is the going topic which we will cover once we are done with the random variable. And this is the same thing which we have seen in many other places. Remember where we talked about independence? expectation of x into y. When we talked about joint distribution, remember we said that x and y distributed, you want to figure out how x plus y is distributed, and depends whether x and y depend on each other or not, right? So this is something which intuitively makes sense. We will formalize it. There is good reason now for us to formalize this concept, and this will be formalized using conditional probability. How many people have seen conditional probability before? Okay. Okay, good. So then I think it will be easier to go through conditional probability, and then you can define independence. But important point again, coming back to normal distribution, if you have a random variable x which has God knows what distribution, if you repeat it multiple times, independent, in some sense independent, and then I talk about this average outcome, then what do I know? Y behaves like a normal distribution, and it will behave more and more like a normal distribution as n tends to infinity. Okay, this is a very, very strong intuition, very, very important intuition to have. This is formalized using something called central limit theorem. You can read about it. I encourage it to you. We don't use central limit theorem as such in computer science a lot, or probably not, at least not in this course. We won't talk about it except we won't talk about the formal statement except just this intuition, but we will see variations of central limit theorem multiple times. Okay, these are law of large numbers, Chernoff bounds, and things like that, which are much more common in computer science. We will see that, but you should know what is the essence of central limit theorem. Okay, and this is a very, very nice essence. This basically says you start with any property. If you look at the average of that property, it will always behave like a normal distribution. And this, the conditions on x1 and x2 could be relaxed. You get some weaker bounds and things like that. But again, that is for later, right? So that is why normal distribution is important. Anytime you look at an average property, you feel that the thing will look like a normal distribution, like a bell curve, right? And what is this point? Expectation of x. Okay, so this is what we did last time. Let's look at what we want to go through this time. What is on y-axis? Okay, you tell me, what am I plotting? F of x is what is it called? Probability density function, right? So I am saying what value your random variable, what probability is of x equal to small x. Mm-hmm. Variance is captured by the thickness of this curve in some sense. Okay, how thick this curve is. If this is wider, and you can think about it, right? If you look at the bell curve, a point curve, this has expectation at this point, and the variance is 0, right? And as this curve becomes wider, so this width in some sense captures the variance. Good question, right? Okay, great. Let's start the recording. Let's start a new topic now. Okay, I think recording was already going on. Great. So before we go to independence, conditional probability, I want to talk about another example, which is just about simple random variables, called Buffon's needle problem. And it's a very, very nice example. It shows the power of the concepts we have learned till now. Okay, I will tell you the problem. I will give you some time. I will try to finish today's lecture faster because you have a quiz in the evening, and that's kind of 15 minutes of the class. But before that, let's try this problem. Okay, how many people have seen this problem before? Okay. Okay, good. In the first lecture, right? So the problem was you have an infinite plane, you have parallel lines drawn at the distance of 1 centimeter, right? And now you take a needle of length 1 centimeter. I will make your life easier. I will say it is just 1 centimeter, right? And drop randomly on the plane. Okay, what is the expected number of intersections with these parallel lines? This is the question I am asking. Okay, again, the plane is infinite. Let's say parallel to x-axis, I have lines at every 1 centimeter interval, right? And then I drop a needle. So first thing, let's say x is the number of intersection. This is the random variable whose expectation I need. What values can x take? Just to make sure you understand. Right? 0 if the needle falls like this, 1 if the needle falls like this, and then 2, you have to do a lot of hard work to make sure it has 2 intersections, right? And then you want to find expected number of intersections, correct? What should we do now? How should we approach this question? Okay, right. So intuitively, what you want to do is you want to define what do I mean by randomly dropping the needle. In other words, what is my sample space? Right? That could be done by probably fixing one point, or it can be done the way I will do it is, I will say that look at my needle, look at the midpoint of my needle. I want to ask, where does that fall? Yes, in some sense, it can fall at the infinite plane, but I want to use symmetries and simplify. I will say, look at this line of length half. Right? My needle's midpoint will lie somewhere between this point and this point. Make sense? Right? So again, here there is no trick involved because I'm just defining the sample space. So I'm defining the question in some sense. I'm defining what do I mean by randomly dropping it. The definition of randomly dropping it is when I drop my needle, the midpoint falls somewhere between at a distance of 0 to half from this line. And obviously, one more parameter is the angle which it makes, right? And I will say that the angle can lie from -pi to pi. And then, you could have taken the entire distance from 0 to 1. You could have taken the entire circle, but with symmetries, you will get the same answer. So just to keep my life simple, I have defined now the sample space. Okay, my sample space is like a rectangle. And any point I'm throwing a dot at random in this rectangle. Okay, this has defined my experimental field. Right? Now, do you want to take a try and say what is the expected number of intersections? So obviously, first we have to fix the probability density function. What is the probability density function? If I am throwing my dart randomly at this rectangle, it's uniformly at random, right? I'm throwing uniformly at random. If the interval was of length 0 and 1, what is the probability density function? Okay, this is interesting. So I think few points needed for. So I put a point randomly between 0 and 1. I'm choosing a point randomly between 0 and 1. what is my probability density function? What do I want? In the interval of length theta2 minus y2 minus y1, my probability should be y2 minus y1. So what is the function which you integrate? So integration fx dx y1 to y2 should be y2 minus y1. Can you tell me fx? 1. That's all. Good. Right? In general, when someone asks you a question in mathematics, if you don't know the answer, your guess should be no. Your answer should be 0. If 0 doesn't work, then try 1. Most of the time, you will succeed. Okay. Anyway, jokes apart. So if in this case, my probability density function should be 1. Now you don't have to take a random guess, right? You understand why it is 1. Correct? Now, similarly, in this rectangle, my point is, if I take a circle of area, let's say 1, what should be my probability of hitting this circle? 1 divided by the area of the rectangle. What is the area of the rectangle? Pi by 2. Great. So then what should be fx theta? Think about it. Use your pen and paper. Sorry, is there an answer? Try it. There's nothing, no problem with being wrong. But dx d theta to baad mein aayega. What is the density function? It's a number. It's not even related to Buffon's needle problem. Okay. What I'm asking now is, you have a rectangle like this. I'm throwing a dart randomly, uniformly. What is the probability density function for this experiment? 2 by pi. Good. And again, it's the same thing. If you integrate it over an area, right, it's some constant times the area. And the constant has to be 2 by pi. When I write it, okay, again, if I choose a random point in the interval 0 and 2, right, what should have been my probability density function? Is that clear to everyone? Is there a question about this? Now you see, similarly, if I'm doing it in 2 dimensions, if my probability should just come out as 1 by area of the rectangle, that is what exactly I want as my probability density function, right? So great. Now I have taken one more step. I defined the sample space. I have defined the probability density function because it's a continuous random variable. Great. Now, what is the expectation? Again, you might ask, what if this needle falls flat on the x-axis? Then how many intersections are there? But do we worry about it? Why? The probability is upon this, right? So we won't worry about that. So actually, we only care about 0 intersection and 1 intersection. Even the 2 intersection will only happen at a point. Let's not worry about it. So you want to find the criteria when the needle will intersect the line, right? I ask meaningful questions. You have to look at the slide, right? Tell me. Simple trigonometry. So any answer? Sin theta by 2. Okay, I thought I got a slightly different answer. Probably you defined theta as 90 minus theta or something. But yeah, similar. Sine? What you should get is x less than half cos theta or sine theta, depending on how you have taken the theta. Huh? Half sine theta, because I might have, or you might have, or I might have taken theta as 90 minus theta. But that doesn't matter, right? And then the expected number of intersections is this quantity, right? Because essentially I want to talk about the area in my rectangle where I have one intersection, right? This is the kind of the nice thing about indicator random variables. If x is an indicator random variable, what values does it take? 0 and 1. So what is the expectation of x? That's all. Probability of x is equal to 1, or probability of the event happening, right? You can see it in multiple ways. You can say that I have a 1 sitting behind fx theta, but basically I want to calculate with what probability my needle will hit a point so that I have one intersection. And since it happens from 0 to half cos theta, my theta ranges from minus pi by 2 pi by 2. I have to integrate that. And that's a simple integration. You will get 2 by pi. Again, it's an integration. That means who will do it? Great, right? But actually, this is that simple integration. Even I can do it, right? So let's not worry about it. But you agree that you will get this expected number, right? You will get that the expected number of intersections is 2 by pi. Was it fun? And the scale of 1 and 10, how much fun was it? 5, 6. Okay, let's make it more fun. What if the needle is a W? How many intersections will it have? You want the angles and everything? Will that help? What if it is a circle? What if the needle is Y? Suddenly the fun doubled. It went from 6 to 12 out of 10. So when there is no hope, the hope comes from linearity of expectation. If you have seen the lecture notes, then don't answer. Okay. I know, unfortunately, I kept the quiz today, so you have gone through the lecture notes finally, and many of you might have seen it. But if you've already seen it, then don't answer. If you have not seen it, then great answer, yes. What is going to help is linearity of expectation. And you will see now, this is again one of the proofs from the book, or one of the most beautiful mathematics I have seen in my career, right? Few examples, I'll take 10 examples. This is very nice. So what is the idea? This was actually, there was a TIFR professor who gave a lecture here, and he explained this to us. It's very nice. This is just one example. There is an entire theory of it. Now, instead of this, you can have a globe where you are hitting the random point, things like that. Find the areas of countries and multiple, anyway. But this is, let's worry about this, right? What happens? How we can solve this? First, some claps for my awesome drawing. Come on, it deserves a clap. I took a lot of time in drawing that. Thank you, right? So, and it's clear that the essential idea is we're going to divide the needle into very, very small parts. Okay, how many small parts? N tends to infinity. We'll worry about that later. But let's say if I have parts from 1 to n, and look at the ith part, then define xi, this is the random variable now, which is the number of intersections for the ith part, right? X was the total number of intersections for the needle. Xi is the number of intersections of the ith part. Then do you agree with this statement? Be careful, I always trick people. No, yes. How many people for no? Okay, so majority is right in this case. How many people for yes? Now everyone accept. Okay. Yes, clearly, right? So in this case, it's easy because think of it in two parts, right? The number of intersections of the needle, because the parts are disjoint, the small parts, then the number of intersections of the entire needle is equal to sum of the intersections of the individual part, right? So then what do I know? Expectation of x is equal to summation over I expectation of xi. Notice here, the xi's hugely depend on each other. They are not independent in any sense, right? Remember, I was talking about a W needle, right? And then saying whether this part intersect or this part intersect clearly depends on each other, right? You can't say that they are independent. Similarly, this part and this part intersects, right? They're not independent, but I don't care. Still, I can apply linearity of expectation. That is the strength. And once I know this, then you have to take a small leap and say that means E of xi should only depend upon. So notice that these intersections can become smaller. And then it doesn't matter whether there is a turn or not. It should only depend on the number of small parts, or in some sense, the length of the, and nothing else. Okay, so this is a leap. I understand. I will give you a minute to think about it. Since this is there, and when you talk about smaller and smaller and smaller part, what you are saying is that EXI only depend on the length of the needle. Sorry, E of X. It doesn't, again, I'm not saying X only depends on length of the needle. That's clearly false. How my W falls, how my circle falls as compared to how my needle falls are going to be very, very different. The distribution is going to be very, very different. No way the X is going to be the same. But because of linearity of expectation, I can say that the expected value of X should only depend on the length of the needle. Number of parts, and now if you put number of parts to be some small length, then it is total length of the needle. That means I can say that expected value of X is some constant times length. Are we okay with this? Okay. So when you stare at me like this, I don't know whether you are okay with this. It is too simple or it is too hard. Yes. Exactly. Linearity of expectation. The linear word in expectation. That's the same thing, right? You will sum up the individual parts, the length, and then if the number of parts are so C is in some sense the number of intersections for the unit length, and then unit could be very, very small part, so that you don't have to worry about the rotation, and then it is just C times the M, right? Very nice, very good question, right? When I said depend, I meant linearly depend the length. And it's clear why, linearity of expectation, right? The same linear is coming. Okay, don't shout out the answer. I want all of you to take 2 minutes and write in your copies what is C. Don't tell your friends, don't help out. Now just think about it yourself and write the answer. What is the constant here? How will you figure out the constant? How many people figured out the constant? Okay, so this is probably you're not thinking of this in terms of, I don't know, high school or something. When you have to find the constant, the idea is to look at one example, right? And which example do we have? One needle, right? Using the calculation we have already done before. We know that if the length of the needle is 1, then the expected value is 2 by pi. That means C is equal to simple. But what if you are like me and hate integration? I have removed one integration by linearity of expectation, but for this constant, I would say, oh, you made my life hell. I had to go to this, and not just integration twice, right? With x as well as theta. Sorry? So think about it more and give me the exact answer. Semicircle? Okay, how will you do it with? Semicircle needle will give value? Why? So semicircular, okay? You mean this, right? Oh, sorry, what does it mean? Isn't this semicircular? Okay, okay, you mean circular, right? Brilliant idea, right? What if my needle is a circle of diameter 1? If I drop it, what do I know? Number of intersections is 2. Like, I don't know how you will drop it so that you get to one intersection. Right? Okay, let's decide it by democracy. How many people think number of intersections will be 2? Okay, how many? 1. Who shouted 1 then? Okay. Anyway, so yeah, so now you know a very, very easy way to find the constant. You know that the semicircular, not the semicircular, the circular needle will have expected value 2. And length of the circle with diameter 1 is so 2 is equal to C times pi. And now this tells you that the expected number of intersections for a needle is 2 by pi times the length of them. That needle could be W, needle could be circle, needle could be straight, needle could be like my face. I don't know. I don't care. Actually, face is not correct. I need a one-dimensional needle. But any one-dimensional needle, any shape, I can still figure out expected number of intersections. Remember, X is still hard to figure out. That was the reason why the traditional way of taking expectation would have been. But expected value can't turn out to be very, very easy. Okay, this is Count Buffon. He was a French count. His problem, very nice solution, and there are extensions to it. Feel free to read about them, discuss them on Hello, your point. But I hope you find now that linearity of expectation is very, very strong. Questions about what we did till now? Happy with Buffon's needle problem? Happy with linearity of expectation? Again, there is another example of linearity of expectation which I have not covered, which is there in lecture notes. How many people have seen it now? See it. Okay, it will help you. It is about, you have the simple problem is, let's say you are a fan of, when we were young, you look at, you go and buy a chewing gum and it has a sticker numbered from 1 to n or for n players, and you want to collect stickers for all n players. How many chewing gums do you need to buy? On expectation, right? Obviously, you can't give a single number, but when I say how many in expected numbers, how many times you need to buy the chewing gum to get all possible stickers. If you haven't seen the solution in the lecture notes, try it. And you will see that it's very hard, but linearity of expectation will solve it. And you should also think about a way in which it is wrong. I think in assignment I posed the wrong way also, but yeah. Okay. Enough about linearity of expectation. I think you must also be tired. So let's switch the topics. In many places, we actually saw one thing which was important for us, which we wanted to quantify. What was the point? The question written here. It could be in terms of random variable, it could be in terms of events. We will start with events because they are simple. The point is, if some event has already happened, let's say you toss, you roll a dice twice, and then you ask, what is the value on the X? Is the or what is, if I get the 1 on my first roll of die, what is the probability that I get a 1 on the second roll of die? And those should be independent. But if I say, define the events with the same, then they are obviously related. These were the two extreme cases, but things can lie in between, and you want to quantify that. This happened in joint probability distribution. This happened in normal central limit theorem when you want to talk about independence, right? This happened when we wanted to talk about expectation of X times Y. Multiple places we want to capture this. And let's see how we formally capture it. This is for simplicity. This is just so that we have the idea of the definition. Suppose this red rectangle is my universe, and for the sake of simplicity, let's say that I'm hitting everything uniformly, right? Uniform distribution. A is some event which is described by one circle, B is event which is described by another circle. Now if I ask, I know that B has happened. What is the probability that A is going to happen? What should that be in terms of the areas here? Very good, right? This is quite kind of obvious, right? So as I say that event B has happened, that means my universe has shrunk to this circle, correct? And then if I want the probability of A, that means I'm interested in this area, right? And if I had given to you this question, you are hitting a needle uniformly in this circle, what is the probability that I hit in the shaded area? You would have said shaded area divided by area of the circle, right? And just extending it, instead of area, I can talk about probability of the intersection. So probability of A given B should be defined, or we will define it as probability of A intersection B divided by P of B. This will obviously only make sense when P of B is greater than 0. So I will assume this, okay? Because then otherwise it takes us into boundary cases and many problems. We'll just assume that probability of B is greater than 0, right? And then this is my definition of conditional probability. Probability of A given B is probability of A intersection B divided by P of B. And now, if you understand this idea of conditional probability, let me ask you a question. We will define it once again. What should mean by saying that A is independent of B? A should not, if A does not depend on B, what should it mean in terms of these probabilities? Don't go into A intersection B, A given B. Right. So independence should mean probability A given B is probability of A. It doesn't matter whether B has happened or not, the probability remains the same. Is it a guess or is it a proof? Because if you do this, this is a proof. If you say this is a guess. Okay, this is true. I will leave it as an exercise. This again shows that in some sense, our dependence thing is kind of same, right? Anyway, we will come to independence. I will spend a lot of time on independence of random variables, independence of events. But let's worry about the simple question of conditional probability. Answer this question very fast, or not very fast, but fast enough. We can. Okay, good. Why? Because probability of what is A? 2 coin tosses. So 2 heads, sorry, not 2 coin tosses. 2 heads. B is at least 1 head. Good. What is probability of A intersection B? 1. 1 point in the sample space. 1/4. Both heads, right? H. Right? And probability of B is? Who said half? 3/4, right? HT, TH, HH, right? At least 1 head. That means probability of A given B is 1/3. Okay, let's do one more small example, which will tell us a good principle, and then we are done, right? I don't know whether this is clear from the picture, but the idea is that you or a kid goes to 2 possible machines. First is the red machine. It is defective with probability half. In the red machine, the probability of defective is 1/4, right? What if the kid really likes the blue machine and picks it with twice as much probability? Then what is the probability that a picked ball is defective? Is that good enough information? Do you need any other information? Is the question clear? Right? So then tell me the answer. Right? Either you will pick a red machine or a blue machine. If you pick a red machine, so what is the probability of picking a blue machine? 2/3. Probability of red machine, 1/3. Good. Now knowing this and knowing that this is the probability of defective in a red machine is half, probability of defective in a blue machine is 1/4. How will I do it? Okay. The probability of red plus probability of blue, which is 2/3 into 1/4. Right? What did I do here? This is intuitively correct, right? Seems correct intuitively. If in 12th class I had given you a question, you would have done it. But now with all the last 2 weeks when I've tricked you, suddenly this might seem, but nothing. It's actually very simple. What have I done? Probability of my event is probability of A intersection blue ball plus probability for blue machine, probability of A intersection red machine. Why can I like this? Because blue and red are disjoint and cover the entire thing, right? These 2 events are disjoint and they cover the entire thing. That's why I can write it. And now what is this? This is what we just defined. Right? We can just write it in terms of conditional. That is what we did intuitively. Everything makes sense. That's a good thing about conditional probability. Most of the things will make sense intuitively. And then I will trick you again. But this is fine. There is no trick here. Sounds good? And this I can generalize. Given any BIs which are disjoint partitions of sample space, I can always write my probability like this. This is a very, very important way to find probability of events. And this you have used 100 times. I am just writing it on the board in front of your eyes for the first time. So it should not surprise you. But you should know that this is fine. This is mathematically we know how to prove this. What is important? BIs are disjoint and they partition the sample space. 2 points. If that is the case, then I can find out the probability of an event by distributing its probability into when event B1 happened, when event B2 happened, when event B happened. And the example of it was just now, right? The red machine. Next time, we will see another example. Good luck for your quiz. It is online, obviously. It is not here. Log on to Hello, log on to Zoom, and then we will go through the quiz. Okay? I will end the recording now.